Okay, let's talk a little bit about the electromagnetic spectrum, which I'm just going to call the EM spectrum. And then we'll do a practice problem or two about this EM spectrum. So when we say EM, the EM stands for electromagnetic. So there's really two different waves that make up this spectrum. So one is an electric wave and the other is a magnetic wave. So there's two components that make this up. So electromagnetic spectrum are all the different electromagnetic waves that there are, which is really a fancy way of saying light. Electricity and magnetism are linked together, and then the way that they're linked together is in the form of light. And we have a huge spectrum, right? A huge spectrum of waves, all the way from very long radio waves that go to visible light, which is what we can see with our eyes, and then all the way to the shortest wavelengths that we know of, which are gamma waves. Those are very high energy, high frequency waves. So, and you have more information in your notes about that. When we talk about the electromagnetic spectrum, we recognize that all of these waves travel at the speed of light. And the speed of light is kind of a special speed. It's actually abbreviated with c. And the speed of light is constant. It doesn't change. And it is very fast. And when I say very fast, I mean there isn't anything faster, right? It is the fastest speed that there is. It's the speed limit of the universe. And it has a number. And so the speed of light, c, roughly rounds to 3 times 10 to the 8 meters per second, which is 300,000 kilometers per second. I mean, that's so fast. Now we talk in miles, so that's just over 186,282 miles every second. And to give you an idea of what that is like, if the light could bend and travel directly around our planet, then it would go around our planet approximately 7.5 times around Earth in 1 second. I mean, that's just unimaginably fast. But that's what we're talking about when we're referring to the speed of light. Now, when we talk about waves, we have a wave equation. And this wave equation we've used before, right? The wave equation was velocity is frequency times wavelength. So remember that this is for wavelength, right? That's a lambda. And frequency F and V for velocity, those make sense. But when we have something that looks like this, a Greek letter, sometimes we get a little confused. So we have basically the same thing that we can use for light, and I'll just call it the light equation for right now. And it's basically the wave equation with one exception. Because the speed of light is going to be constant, then we have c equals frequency times wavelength. And that is the wave equation. And we will do wave problems and speed of light problems the same way. The only difference is we're going to use c instead of v. It also means that we have our old triangle trick again that we can use. C goes on the top, frequency and wavelength go on the bottom. So what I want to do is I want to do one sample problem. And this sample problem is from your worksheet, right? So this sample problem is going to be number 3 on your worksheet. So if you get out the electromagnetic spectrum worksheet that's posted online, I will read the problem and then I'll do that out for you right now. So the problem reads, it says calculate the wavelength of a violet light with a frequency of 750 times 10 to the 12 hertz. Now, oftentimes when we're dealing with speed of light problems, the wavelengths can be very, very small and the frequencies can be very, very large. And so for that reason, oftentimes we will use scientific notation. Okay, so this is going to be number 3 from your worksheet. So because it's a light problem, we can always write c, the speed of light, 3 times 10 to the 8 meters per second. And we want to find the wavelength in this problem as it reads. And the frequency is given. And so the frequency of this problem was 750 times 10 to the 12 hertz. So that's a very high frequency. Now, if we look at our wave equation, as I have it written here, C equals frequency times wavelength. I'll just rewrite it. C equals frequency times wavelength. We can see that's not going to quite fit because we need this to read lambda equals. So you can use a little bit of algebra, or you can use your triangle trick. And we've got lambda equals C over F. This is the equation that will solve this problem. And now all we have to do is put the numbers in, and we can use our calculator. So we've got our 3 times 10 to the 8 meters per second, and we're going to divide that by 750 times 10 to the 12 hertz. And if you have a scientific notation function on your calculator, you can put these right in. Otherwise, you might want to use a little bit of parentheses, or you can do it out using the rules for scientific notation. So when we do this, and we put these numbers into the calculator, my calculator gives an answer of 4.0 times 10 to the minus 7 meters. So these problems are done pretty much exactly the same as we would do the wave problems, but remember that the exception is now we're putting in c for the speed of light in place of v for just any velocity. So there you have it. The rest of the problems on that worksheet, on the electromagnetic spectrum worksheet that I gave you, they're going to be done exactly the same way. You're either going to have to solving for the wavelength, which is lambda, or the frequency, which is lowercase f. Let me know if you have any questions.